So in this vlog post we're going to look at compute and geometry shaders in Unity. Request was made by Paul Ward. Example of how to produce a mesh and render entirely on the GPU using direct connection between a compute shaders buffers and the mesh buffers, if it's even possible in Unity. Well, I think it's possible in Unity. I think that's what I've done in these samples. Excuse me. But what I'm going to do, I'm going to cover geometry shaders first, because I think if I can show you what we're trying to render at the end point, we can then move back to the compute shaders and see why I'm creating the data in that way. So in this particular script, you see we've got quite a few objects in there, but we're just going to look at the billboards for now. In this script, we're going to render a single billboard, just using my geometry shader. We can give it any old sprite we like. At the moment it's using my logo. For Charles will code it. We can set the size, the colour, wind we'll discuss again later on. We've got a billboard type. Yeah, if you don't know how, there's different ways of rendering billboards effectively. So I've implemented static billboards, which means they don't follow the camera, cylindrical billboards, which do follow the camera, but they have the y-axis locked. So for things like, I guess, grass, maybe raindrops, stuff like that, we can use a cylindrical billboard for that. And then we've got spherical billboards as well, which basically face the camera regardless of whatever direction it's in relation to the billboard. So as you can see, there's no mesh renderers, no mesh filters, nothing like that at all on this. So it's all basically passing loads of points to the geometry shader. The geometry shader then builds the vertices on the GPU and renders them. So let's have a quick look at that in action. So we've got a single. So if I move my camera, this is set to static mode. Yeah. So billboard type. Oh, the tooltip's not coming up because it's in running. So it's at 0, which is my static version. So we have a look, and again, this can be anything we like really. So let's use that because it's a bit more, it's easier to see. Yeah, so we've got a nice little snowflake, nice and festive. So it's nearly Christmas. Yeah, so that's a static billboard. If I switch this now to cylindrical, so basically I can go all the way around that billboard, and as long as I'm not going above or below it, it'll always face me. So if I go above it, let's get a bit of height. See how it's not. So as I go past it, it tries to rotate, but it's not rotating on the. It's keeping that y-axis pretty much down. If I switch that to a spherical billboard, now no matter where I am, it'll always be facing me. So I can rotate all the way around, and just to illustrate that point again, if I go back to cylindrical, so it's not quite it's not following me. It's locked. That y-axis is locked for it. And then if I go back to static, that's not even rotating around any axis. It's just sat there in space. So let's have a look at the script itself and what it's doing. Excuse me. So I've got the geometry shader that I'm going to render it against. I still need a material to apply the shader to, with the sprite, the size, the colour. I've got a compute buffer set up, but it's not using a compute shader to populate that buffer for this example. So I just want to show you how it's going to take that compute buffer and use it on the GPU. These are used in the weather effects. I'll show you those again later on. Wind, again, that's to do with the weather. So I can set my billboard types, the points that I'm going to render, which is I'm just using to populate my output buffer. So on start, basically it sets up the material, and then I'll populate the points. At the minute I'm just populating one. I'll change it to those 5 actually, and we can see it render. And as you can see, all I'm giving it are 5 vector 3s. So I'm not giving it 4 vectors per quad that I want to render. I'm just giving it 1, which is effectively the center of the billboard I want to render. use compute buffer data. We're not using it, so it's going to set the buffer up, and the buffer is the length of whatever the amount of points we want to render, and then it's the size of 12, so the stride for each element in that buffer is 12 bytes, because we're using 3 floats, 4 bytes each, so that gives us 12. And then we just set the data on the buffer. Now, using a compute shader, we won't have to do that, but I'm just doing this to show you what the geometry shader is doing with these points. Again, ignore that bit for now. So we set the material up, set the pass, the color, the buffer, we pass it in, the sprite, the size, billboard type, the transform matrix for that's important because we're not rendering it like a regular mesh. You've got within graphics, I think. Yeah, IntelliSense is working, cool. So we can draw mesh now. I always press the wrong key with these fat fingers brilliantly. Draw mesh now. Draw procedural, indirect. So there's a few ways we can render stuff in Unity. We're doing draw procedural because we're handing in these points. We can say the kind of topology that we're pushing, which is going to be just points, so just vector 3s we're pushing in, and we're going to output. And then the amount of points that we're going to be rendering. So how does the shader deal with these? So the shader effectively has just got all the properties set up for it. I've got a regular blend, alpha blend. I've switched the color off so we can see the backs of them. Z right's off because this is for like a particle, I guess, used for in a particle system. So you don't want the Z right, otherwise with your blending it'd look really odd. Target's 5. I think it has to be 5. I don't think you can render geometry shaders on anything lower than 5. As you can see, in like any other vertex fragment shader, we've got a vertex shader and a fragment shader, but we've got an addition of a geometry shader as well. And I've also got a pragma for compiling fog. I've implemented fog in this just so I could see what it looked like actually, if I could do it, and I've got it working with fog as well, which is quite cool. So that's not really for the geometry shader, it's just for rendering fog. And then we've got all our values set up there with some defaults, a data structure, we've got an input structure, a structured buffer, which is what we're going to use to populate, that gets populated from the compute buffer. So if we've got buffer points, if we look back at the shader script, buffer points is what we're loading with our output buffer. So then we've got an input structure as well, which is what we're going to use to pass data about. So we've got a position, UV, and then that's for setting up the fog coordinates, so Unity can render fog against it. And then our vertex shader, we're going to output an input structure, which pos, UVs, and fog. And instead of getting like a regular Unity app data structure coming in, we've just got an index, an unsigned integer. So a vertex ID effectively, because we're rendering points. So the graphics card is going to hand onto our vertex shader the ID of the point we want to render. So now we can use our buffer that we've passed in with our points in it. We know the ID for it, so we get the position because that's what we'll set in our output structure, and we add the world position to it. We're not going to multiply it by object world. I forget the Unity default name for it, but effectively we're adding the world position to the position we want to render, because we're going to handle all the rotation and everything in the shader. So we'll look at, which is what this method does actually, but we'll look at that in a moment. Then we've got the geometry shader. So we've got to tell the geometry shader what's the maximum number of vertexes it's going to push back out, and I think that's just so the graphics card can allocate memory, it can optimize it a bit better. So we've got an input point P coming in, it's an array of one point effectively, and we've got coming out is going to be the triangle stream that we want to be writing our new vertices to. So the vertexes we create, we're going to write to the triangle stream. So we've got the size for our vertex, for our billboard, so the dimensions left, right, up, down, and then we've got basically a float for each of the vertex points that we want to render. So obviously we're getting one vertex point in, we now want to create 4 vertices, so we're getting 1 position point in, and we want to render 4 vertices to create a quad. So obviously you can create any kind of geometry in this. We could be creating triangles, we could be creating pyramids, we could be creating cubes, you could be creating whatever we want to create in here. But for this particular purpose, for the billboard, we just want to create 4 points. So if it's a regular static spherical, so we don't want any rotation or anything, basically we're taking the position and we're adding and writing to each of the 4 coordinates, 4 vectors, the position plus the half offset. So this one is going to be the size, so basically the size of the billboard we want to render. So the half offset is going to be so it's going to be the top left corner, that's going to be the bottom left corner, that's going to be the top right and bottom left, I think. But anyway, they're your 4 corners that we're going to render. We don't want to push anything into the Z because we're not going to move it around down the Z coordinates, and the W is set to 0. If you set it to anything other than that, you'll get some really odd rendering effects because it uses that W for what's called the homogeneous divide on the basically moving it into screen space. Excuse me. So don't put anything other than 0 in there. So if it's not spherical, it's going to be either cylindrical or spherical. So if it's a static, if it's not static, it's going to be cylindrical or it's going to be spherical. So we kind of need to know what the up vector is. Again, ignore wind, but we can basically, what I can do is give it a wind value, and that'll rotate the particle to the direction of the wind. We need a look direction, so basically where the camera is in relation to our position. If it's a cylindrical, yes, remember value 1 is a cylindrical billboard. If it is cylindrical, we're going to lock the Y coordinate, so we're not going to rotate against that at all. We're going to normalize the look, and then we need to find out the right and left coordinates, so we can get the right coordinates, so we can get a cross product with the up to get the actual rotations we need. And then on each of the 4 corners, I can apply my rotation point function to it. So it takes the position in an offset, which is basically where we want to move that point to. So one for it's different for each of the corners. We've got the side vector and the up vector, and basically all it's going to do is, with the positional data, is rotate that point by the side and up vector effectively along the X and the Y. So that then gives us the rotated quad effectively. So now we want to push this vertex information into the triangle stream that we've got passed in up here, and to do that we just set them up. So we're going to multiply now by the view projection against the positional data we've just set up the UV for each of the points, do the Unity fog stuff, otherwise it won't render the fog, and then we just do the triangle stream append. So we're just appending input structure, as we can see it's of type input to the triangle stream, and we need to do that 1, 2, 3, 4 times. So that's 1 for each of the corners. So once it's done that, it then gets passed on to the fragment stroke pixel shader, where all we're going to do is get the sprite, the UV value for each one of these 4 points, and multiply by the colour, apply the fog, and then spit it out. And that's pretty much it really for the geometry shader to give us this effect. So let's have a look with what do? We changed it, didn't we? Let's have a look. So we've got 5 on there. See what that looks like. So now, no matter how many points we pass in, I forgot to save. Oh, I keep doing that. That's driving me mad. Double clicking. I've gone absolutely click crazy. So we've got our static flakes. So there's 5 of them now. You see, because we passed in 5 points. And as I say, we can colour these however we like. Do whatever we like with them. Set the alphas. We can change the size, so we could make them taller. Yeah. Do pretty much whatever we like with these now. you're not really going to see it if I show you the wind, but yeah, so I'm going to set them to spherical. So that's the billboard shaders. So now let's have a look at how we change and alter that point data in a compute shader, and also have a quick look at what compute shaders are and why they do, why we're going to use a compute shader effectively. Right, so I've got, let me just disable that. Minimize that. So let's have a look at this compute object, make it active. So this is just using the compute shader now. Well, let's have a look at what a compute shader does. Let's get rid of that. So thanks to Microsoft's awesome documentation, I managed to steal this image from the compute shader docs. So basically, a compute shader is a way of rendering shaders, or rendering data in threaded groups. So you can set up a number of work groups, and in each work group is a batch of threads, each thread being your little bit of compute shader that runs. So it gives us kind of a funky coordinate system to get at and to know which particular thread we're actually working on within that compute shader. So in this case, they've set up 1, 2, 3, 4, 5 by 3 groups. So they're dispatching 5 by 3 by 2 actually. So there's a Z coordinate on that as well. And within each of those, there's so they've got a 10 by 8 by 3 set of thread groups. So in each one of those, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 30 thread groups running. In each thread group, that even says there, look, I should really read the document. So that's 30 thread groups, and in each 30 thread groups is 10 by 7 times 3 sets of threads going. So that's that's quite a lot, and that's all happening at the same time. So you can kind of appreciate, if you've got massive amounts of data that you want computing rapidly, then compute shader is a no-brainer really. If you've got small groups of data that you want doing, then probably a compute shader is not for you. You may as well stick to the CPU, unless obviously your CPU locked. Then I guess you can offload it to the GPU this way. But yeah, it's really for chunking really big lots of data. You'll get more benefit the more data you throw at it effectively. I'm just going to switch off my Skybox just so you can see this, so that hopefully so what I've got is my compute shader. If I show you the script, actually I'll show you the render first, show you what it does. So if I run this, so as you can see, it's rendering a lot of points. I think I'll check in a minute, but I think it's rendering 1 million points. So I've got 10 by 10 by 10 thread groups, and in each thread group is 10 by 10 by 10 threads. So yes, I think that's 1 million points it's managing here. And I've got a little pixel shader, not a pixel shader, I've got a little vertex fragment shader that's just going to render those points on screen, and it gives it the color of whatever it is in world space. I think I add 0.5 to or something, otherwise some of these would be black. I think those white ones over there or maybe those cyan ones. Anyway, I set so that you can at least see them all. So as you can see, that's a lot of points, and I'm hoping you can see it's rendering them pretty quick as well. So if we have a look at the stats, so that's 1 million points, and it's still like 74, 60 75, 76, 69 frames per second. And, you know, the render thread's still 0.4 milliseconds. CPU times 1340 milliseconds. But so I think you can appreciate how powerful a compute shader is just by looking at these points. So if we combine that with a geometry shader, we can take those points and render them, you know, with some decent geometry, not just as points. So let's have a quick look at the compute shader script itself. So yes, I've got my the compute shader which gets passed in. When you create, let me just quickly show you, when you create a compute shader in Unity, where's my shaders, compute, you get this super funky little icon. So you've got to do it with create shader. So you've got the usual choice. So when you do compute shader, you'll get one of those funky little things, and it'll set you up with a basic default. Let's have a look. Actually, I'll just create one. Yeah, so new compute shader. If I double click that, so that's what you get in the basic compute shader. So it's not a lot, is it? But it's geared up for 8x8x1 threads, and it's just got the dispatch thread ID, and using that it can work on the result set, which is just a float 4 result. So I think I've seen a lot of examples of people using them for manipulating textures and things, which is quite cool. So obviously each one of those points could be a pixel effectively, so float 4 being a colour, RGB, and the alpha as well. Let me just get rid of that. But we're going to use as for reload. Use as to get some geometry on the screen. So that's the compute shader set up, ready to go. I've got the vertex count, and I kind of want to know that so I can set up the buffers prior to calling it. As I say, it's 10 by 10 by 10, and then 10 by 10 by 10 work groups. My output buffer, which is what's going to get populated by the compute shader. The shader, point shader, which I'm going to use that's my kind of my debug. So you see where I've got debug renderer switched on there. That's my point shader there. I'll show you that again in a bit. Whether to use debug render. So I've got a function to initialize the buffers. So basically our buffer is going to be whatever the vertex count is, which is 1,000,000. And it's going to be the size of, so the size of floats times 3 for each of the positional data. And then have I got a structure on there? Times 6, because I think I've got color data in there as well. We'll have a look in a minute. But basically it sets the compute buffer up, and then it sets the buffer on the compute shader. You need to know what the kernel is to do it. I think I'll get that in start. I'll show you in a bit. So the output buffer in there is going to be set to buffer, and then if I debug renderer, then I'll tell my my debug shader, give it the points to render. Okay, so I've got a dispatch method. So if your machine or card doesn't support compute shaders, then you'll throw a debug warning and return, so it just won't run the code. So then it just calls the compute shader dispatch, tell it what kernel. So basically in the compute shaders you can have multiple kernels, each kernel being a compute shader in the compute shader file, and then you tell it the thread groups you want to set up. So I think they call them, so thread group X, Y and Z that you've got on there. Then I've got a release buffer again just for tidying up I guess it must be unmanaged to rip it out of memory once it's done with. And then I've got my start method. So the start method gets the kernel ID. So mine's called CS main. If it's debug renderer, then I set up my point material, and then I initialize my buffers. And then just like in the geometry script, I've got my onRender object, and if I'm using my debug renderer, so I'll call the dispatch, get the point material, and then set the vectors for the world position, and then just draw a procedural just like I was with the geometry shader. So you can see we'd replace that with the geometry shader. On disable, then it releases buffers as well. Now I've got my dispatch method there, so that I can call that from another script effectively, and so then that other script will then execute the compute shader dispatch method and populate the output buffer for me. So let's have a look at the compute shader for this. Grid generator. So as you saw in the render, it basically just sets up a grid of points. I think they're all spaced 1 point apart. I can't remember what I set it up as. So I've got a couple of, so that's my kernel setup. Yes, that's the kernel CS main. I've set the thread group size. I've defined those hard coded effectively. I don't think you can set these thread group sizes with a variable. Whenever I've tried that, it always complains about it's not a constant value being used to set the number of threads. And again, like with the geometry shader where you're setting a number of vertices, I think it needs that to allocate memory to do what it's got to do in that particular compute shader. So this CS main is the actual, so that's my kernel. So this is the compute shader that will be ran in each and every single thread. So this bit of code is ran 1,000,000 times, right? So because it's a 10 by 10 by 10 by 10 by 10 by 10 compute shader. Now I'll give it a load of extra parameters. So the group IDs, dispatch thread IDs, group thread IDs, group index, all that sort of stuff, so I can find, basically, it might not be the best way of doing it actually, but it might be my ham-fisted way of finding the index within the output buffer. The output buffer is a read-write structured buffer, so that means I can obviously read and write to it. You can also have append buffers as well, so you can dynamically add as you're going. With those, I think you still have to specify the size prior to calling. So you've got like a max size, but it could be anything up to that max size. But for this, we're using structured buffer, so I can calculate and got my ID of the element we're working on within that buffer. The scale set to 0.5. So each of my dots will be 0.5 apart, and then using that the ID, group ID, and all the other lovely bits and bobs, I can then work out my point space, my points position in space. So it's based on that, and it's also then multiplied by the group size, so I can expand it out depending on not just on the thread group, but the entire work group size of it. And then basically just output it, put it, and then multiply it by the scale, so then it's offset for the size. So that's how I'm creating those points in space in the compute buffer. So that then gets handed on to my point material, which is pretty simple. I think it's a vertex fragment shader. Yeah, so there's no parameters. Target 5, I don't think I need target 5 for this. Oh, I might do actually, because I'm using a structured buffer, which is probably a shader model 5 structure type, and all that this is a vertex and fragment. Data is just position, so vector 3s. Input points, which I just want the position and color. So the vertex shader just takes the ID again, just like in the geometry vertex shader for the geometry shader. Sets up the world position plus world position. Only this time I'm going to multiply in here by the view projection, because I'm not altering it in any way. I'm not creating new geometry, so I can do it here and right here and now. And then the colors, whatever the world position is, and then the fragment shader just literally renders that, and that's it. So what am I adding? Yeah, so if it's less than 0, so if the world position of it is in the minus figures, then it renders green and blue, so at least you can see it rather than just being a black point in space. So you can see that's how it's handling that and generating 1,000,000 points. And what I've done here as well, which you wouldn't have to do, if you look at my compute shader, it's not very, it's not exactly optimistic. It's not well optimized. So what it's doing, literally on every single call, it's doing a dispatch. So that's every frame. It's calculating 1,000,000 points. Now, in this instance, it shouldn't be doing that. It should just do the dispatch once and then render it. So that's bad code. You can see it's not exactly hitting performance because it's all happening on the GPU. So what you would do in this instance would move that dispatch maybe up into your start, so you've got the data set up, and then that's it, and then your pixel, your regular shader can just render it. But if you're animating in that compute shader, so you're altering those positions over time in the compute shader, which is what I'm doing with the weather effects, I'll show you those in a minute, then obviously you will want to call that dispatch method every single frame. So I think it still shows just how powerful it is. My graphics card's gone doolally again. It's because it got destroyed. Cause I think Unity disables the thing when I lose focus. Anyway, so I think you can agree it's pretty freaking powerful. It's whacking out 1,000,000 points, and it's not even breaking a sweat, is it? So let's have a look at. Before I go into the weather effects, actually, let's have a look at creating some voxel geometry. Let's have a look at that. So I've got another object called voxel geometry object. So as you can see now, I'm using a compute shader input and a voxel geometry script. So that's two scripts. So a thing is the voxel geometry script is calling the dispatch on the voxel compute, gets the data, and then it passes that data on to the geometry shader. So if I activate that now, and in this compute shader, I've set it up so basically I'm using some pull-in noise to give me a terrain effect, and I've done it so I can give it a seed. So like in Minecraft, where you can set out your world with a seed and it'll go and generate the same world exactly the same every single time. Well, that's pretty much what this is doing. So it will generate my voxel block exactly the same each and every time. It's really simple pull-in noise class that I think I just googled pull-in noise in C# on Google, found a class. So if this is your class that I'm using, I'm sorry I haven't credited you, but I can't remember where I got it from. I got it that long ago, so I do apologise. So then you've got so you got a seed for generating it, and then the point shader itself, which I'm only going to use if I'm going to debug render, so that could come off, and then the cube multiplier. So that's basically how many thread groups I want to do. So that'll be, so if I do just one thread group, so that'll be one 10 by 10 by 10 block. So let's have a quick look at the compute shader. So the voxel compute shader, putting very similar to the other shader where we've got a vertex count set. Instead of setting it, I set it based on the cube multiplier. I got the seed set and everything else, and that's just basically going to set up the seed in my random function. So we know initialize buffers. So we're setting up an output buffer and a map buffer. The map buffer I'm going to pass in is basically my pull-in noise generated points in space. So again, this is not being animated. So I hope I've done it actually this time. So the dispatch will probably be called once. So this initialized buffer will be called when the thing gets constructed, and the dispatch should only be called once from the geometry rendering shader. So it's setting up the map, which is going to be the same as the vertex count, and then as it loops through, it's going to oh yeah, there it is. There's my noise actually. So so it uses the noise that's generated. So I'm setting my pull-in noise seed to wherever the seed is. So I've got like a float map, and that's just basically a list of floating point values, two-dimensional array. floating point values. So my Perlin noise generator, I'll give it the height and width, and then the octave, which is, I guess, how gnarly that's going to be, the generated noise is going to be. And then using that, I can iterate through and then populate my map with the value. So basically what I'm saying is, if the map value is greater than my current y coordinate divided by the height, then the map value is switched on, otherwise it's switched off. So in this voxel demonstration, it's literally all I've got is there a voxel or is there not a voxel in the voxel point, so whether they're switched on or not. So once that's all set up, so they're either on or off, then I set the data on the map buffer. I can then send my output buffer, which is what's going to be populated by the compute shader, and then the map buffer, which is what it's going to use to generate the voxel data that I'm going to render later on. And I also set the set vector, which is my group size for the multiplier. So that the group size I am using as a variable and passing into the compute shader. I'll show you that. Usual debug, so if I want to render the point material as well. And then transform position, I'm doing that just so I can center the entire voxel on itself, rather than having it render off to the side. Dispatch method's exactly the same, except I've got my variable for the number of cubes I want to render, and then release buffers. So I've got two buffers in there, so they both get released. So my start, get the kernel as before, usual debug render, and then initialize buffers, and then on render object. So if I'm in debug renderer, which I'm not, it will call it every time. So that's basically not going to get called in this particular example. And on disable, release buffers gets called and frees up my two buffers. So let's have a look at the compute shader for that. So this is where it gets a little bit more complicated. We're doing a few more things in here now. So as before, we've got the kernel set up, the hard-coded 10x10x10 thread group size, and then I've got my actual, so it's defaulting to 5x5, the group size, which is going to be at the moment 1 by 1 by 1. So we've got a couple of structures. So the position structure, which I've got the position of it, but I also want to know, because when you're rendering voxels, if they're next to each other or if they're surrounded by other voxels, then you've got no faces that you need to render. You only need to render the faces that are going to be visible. So that's the 6 faces for this point that are visible, and that's either on or off. And then I've got a block struct, which is basically whether the thing's on or off. Yeah, so do I use that? Might be an old redundant bit. Anyway, so I've got a read-write structure, which is my output buffer, but then I've got a regular structured buffer, which is my map buffer. So that's a static buffer coming in. I'm not going to want to change that once it comes in. I've got my params set up as before. You can see the number of threads using the thread group sizes XYZ, which is my 10s. So this will be called 10 by 10 by 10 times. Yep. So it's 1,000 possible cubes. Well, 1,000 will be calculated here. Again, I found my ID in the buffer. Scale defaulting to 1. Calculate the position in space again, just like I did with the other grid. Output buffer, again, the position just gets set as it was. Now we've got the funky bit of deciding whether my cube is next to other cubes and what faces it needs to render. So we've got, like, well, I call the edge rules. So obviously there's 6 faces, and I set them all up, and they're all empty to start with. So if my map buffer is on, oh, that's why I've got that stupid fool block structure, because map buffer is a block structure, so I'm just passing it in, so whether it's on or off, isn't it? So if it's on, so if this particular block we're working on is an actual block and it's on, then we need to do a neighbor check. So basically I need to what's above it, below it, to the left, to the right, front and back, and basically I'm doing the same IDX calculation as I done before, except what I'm doing, so for the top, if you'll notice, I should be moving the Y so moving the y by 1. For the bottom, the y coordinate by -1. The left, then the x coordinate by +1. Right, -1. Same with the z coordinate for the front and back. So that's how I'm getting the coordinates for the blocks around it. And then I can check against that map buffer. So is the one in front of me, is it switched on? If it's not, then I know I need a face for the front. Is there anyone to my left? So if there's anything on the left buffer, then no, I don't need. I do need one. So if there's not someone to my left, I do need one. If there's not someone to my right, I do need one, and so on. So it goes through all the 6 faces, and then the outer edge cases. So that's basically, am I at the end of the cube? You know, voxels. So I'm at the far left, far right, at the top or at the bottom, at the front or at the back. In which case, yeah, I'm going to switch it on because we don't want to be able to see into the cube. And then we just set the render face to faces for that particular element. We'd already set the position for it above, but there we're setting the render face for it. So now you've seen that, let's have a look at the geometry shader to actually then spit that out. Let's have a look at the script first. Again, just like before, a bit like the billboard one. So we've got a geom shader, sprite, the size, the colour. So that's a reference to the compute shader on it. So if I've got a voxel compute shader on me, I'll get the component, sets up the shader material. Do I need to get the data? So the first time in, yeah, we want to get the data. So we called the dispatch once, and I'll do it this way because I know that that's CSO is populated, so I know I can call the dispatch method on CSO. So once that's done, it doesn't get called again. So then the rest is all in the geometry shader. So the compute shader's gone and done its job. Geometry shader then gets passed in the values to then render. Again, just like the billboard really, except missing the sprite type, the billboard type, because we don't need it. And then we're rendering points, and we're using the CSO's output buffer for that menu. So let's have a look at the geom shader for that. So the geometry shader for that, again, very similar to the billboard one. Sprite color size. I've removed all those cutoffs because we want to be rendering regular solid geometry. Target 5 again, we've got a vertex geometry fragment, and I've got the fog on. I'll show you, if I remember, I'll show you the fog once we're rendering it. All the default values set. You've got a data structure of position, but we've also got an integer array of 6, which is the render faces. We've got our points buffer again, which is our structured buffer being passed in. An input structure, so we've got position. We want the normals as well for if ever we do any lighting on it. The UV for the textures, for the texture on it, and then again the fog coords. And then we've got the input to the geometry shader, which is again position, normal, UV, and the faces. So which faces we want to render on. So our vertex structure, so our vertex data coming in again is the index for the point we're looking at. We're going to output to the input input GS structure, which is going to the geometry shader. And so we get the position, we get the point position multiplied by the size of it, and it's slightly different here, but it's effectively doing the same thing. And then the faces data we're passing in, which is the references data, render faces data we've got from the compute shader. Now this, for each point, we're going to render a maximum of 24 vertices, so that's six lots of 4, 6 lots of quads effectively. And again, so the inputs a single input GS, and we're outputting our input stream, which is going to be passed on to the fragment shader. We've got our size set. Oh yeah, that's for the spacings, isn't it? We've got the size set. UVs we set up, so we know what the UV values are going to be for each of the corners on a particular face. We know what the normals are going to be on each of our facings. We know, and then we set up our vertex float forwards at 24 points. So this is going to populate the data for the front panel, so the front billboard, if you like. basically the offsets, so the half offsets are slightly different for each one, so it renders them so front, left, right, back, top, bottom. So that's our cube rendered, yeah, or set up ready to be rendered. We can then have we've got a for loop here, which basically goes through and checks the faces values, and if it's not equal to 0, so if I need a face against that side, yeah, which we calculated in the compute shader, then for each one of the 4 verts that we need to set up, we set it up. So the VIDX is 0, so that's basically where we are in our array of vector point data. We can then pass in the UVs, which is 1 to 4, because you know the UVs will be the same on each face, but the normals will be reliant on what face it's on. So that's from 1 to 6. You do the fog transform on it, and then we do our triangle append that value, move the VidIDX on, so we can move to the next point. And then what we do here, which is quite important, is we restart the strip, and that basically tells the graphics card that my index winding for this particular piece of geometry is finished. You can now start drawing the next piece of geometry. So if it's not a face that we want to draw, then we want to obviously move on 4 points in the point array, because that's going to be our next facing, and that's it. So that's effectively building our boxes in the vertex in the voxel. And then the fragment shader, again, just like the billboard one, there's no lighting on it at all. It's very simple. Get the sprite, multiply it by the colour, apply whatever fog effect, and then spit it out. So hopefully after all that long-winded description, I can show you what it's going to do. So we're just going to multiply one 10 by 10 by 10 cube set, he says, hopefully. I think it's because, yeah, it's down below me. Let's rotate the camera down. Right, so that's based on the Perlin noise generator, a bit of terrain. Right, so we could go in there. If I fly into it, because I've got culling switched off, you know, we see all just the faces we can see coming out the other side. So that's a simple, just a 10 by 10 by 10 block. So if we change that now to, I don't know if we do 2 by 2 by 2 by 2. Yep. It's a little bit bigger. It's still below me, yeah. So a little bit bigger. Perlin noise. I never know whether I'm pronouncing Perlin. Perlin noise function is there, and it's generating. So basically the Perlin noise value for that particular y coordinate is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 0.11 something, and so on, 0.2 something, 0.3, and so on. So let's go, should we go a little bit bigger? Let's go 10 by 10 by 10 by 10 by 10. So that's going to be a million voxel points being rendered. Okay, so that's what a million look like. So that's 100 by 100 by 100 blocks, all rendered. And let's have a look at this. And that's still banging along at 70 odd frames per second, 0.4 milliseconds in the thread, in the render thread. So you can see it's pretty. I mean, that's, and we're not. That's just really the geometry shader that's doing all the hard work. Really, the compute shader has just set up the initial values for it, really. So what happens if we make that a bit bigger, 12 maybe? Okay, I can notice it seems a little bit slower now. So that's down to 40 odd, but still, that's a lot of data it's wanging around, it's processing. And so that's quite a bit of data. Let's have a look at it and see if I can get a better view from the scene view. There's my camera there. Yeah, so it's pretty cool, I think. Kind of quite chuffed with that. Let's have a look with the fog on. Ooh, that's quite cool, isn't it? So that fog, you know, with all that the fog markers and flags that are in there, that wouldn't render like that. It just, if I switch the fog on, it just renders as if there was no fog on. But yeah, it's pretty cool, isn't it? I'm quite enjoying Unity. Right, so let's have a look at let's switch that fog. Oh, it's off because it's in run mode. So let's have a look now at the weather stuff. So back to 10. Actually, let me render this and then I can show you it hopefully later on. Yeah, that's probably about right with everything on. So more weather test effect. Let's have a look at these. So I'd create like a cack little plane that I can oops do. So that I can effectively just see what's going on with these rain effects effectively. So it's literally just a huge plane and then some cubes and an arch I'll create out of more cubes. Oh, that's a stupid Tough Mudder thing I'm doing next year again. So yeah, so just a basic scene. So I've got 3 weather effects effectively. So I've got rain, snowflakes and snowballs. So if you have a look at rain, if you'll see as well, what I've done is my billboards, everything's switched on except for the actual billboard geometry render, and that's because it goes a bit screwy if I switch the whole thing off and then back on while it's running. It just kills the buffers. I think they just die. That's because they get destroyed, don't they? And then it's not getting initialized on start. Maybe if I put that code in awake, but anyway. So if you have a look, at this scene running, so there's nothing happening at the minute. No weather effects are on. So if I switch, is that on rain? Yeah. So if you can see, I've got a sprite for the rain, which is I think I just created like a faded raindrop sort of thing. So obviously you could create some much better artwork than I do in my programmer art. The size of it is obviously thinner than it is tall because it's a raindrop. Colour of it, I don't know, picked a kind of watery colour. And then you've got billboard type, which I've done as cylindrical, and I've told it to use compute data. So basically it's not going to use the data it provides itself. It's going to go off to the weather shader output and pull the data back from that. So let's switch that on. So yeah, now we've got rain. So that, I think I can't remember how many particles I'm doing. I don't think I'm doing 1 million. But yeah, so that's the rain rendering. And because when I look up, you can see it falling. I've also got on the compute shader a speed value as well. So for rain, we want it falling reasonably quickly. But if you want, I could slow that right down and you can see all the particles individually doing what they're doing. And effectively what I'm doing is basically just lerping in the compute shader the position of the particle based on the speed value. So when it goes down, hopefully if I go down to here, you should see that they disappear as they get to 0, and that's because my lerp function is just basically moving the particle back up to the top of the render point, which is all the way up here. Let me get that back up to 100. Let's get to the top of the rain, where the rain starts. That's a long way up. Make sure I'm moving. Yeah, I'm moving. So if we get to the top, you can see where they're being spawned effectively. This might be quite a cool Starfield type thing. So you can see that's where it's spawning the raindrops. and they come falling down. So if I slow them down again, excuse me, I think I've got a horrible cold coming, that's not good, is it? So if I slow them down again, I can now show you as well the wind effect as well. So basically you can give the wind a value, obviously not y, and what it will do is it will angle, I think it's key, it will pull its value from here. Yeah, so when the wind's blowing, the compute shader applies the wind value to it, so it pushes the rain across as it's going, and also the billboard geometry angles it to the direction of the wind that the wind's blowing it in. So that's what the wind stuff does, which I thought was quite a cool thing to do. So I'll put that back up to 100. So we've got rain. Let's get back down to, actually what I'll do is I'll just go 0, 5, 0, 0, 0, 0. Right, so that's my rain. And again, we can colour it whatever we like. The rain, black rain, horrible rain. Maybe it's a toxic acid rain. So yeah, you do pretty much whatever you like with it. What else? Was anything else? Yeah, the size. So that's big rain. Don't want big rain. And then, so if we switch that off. Oh, actually, let's have a look at the frames per second again. Yeah, so again, still it's not even impacting on it. So if we nuke that, let's have a look at the snowflakes. So now snowflakes are using spherical billboarding. They're much slower. The spacings have changed as well, so you can vary the spacing between the particles. I'm sure you can do that on the rain as well. Yes, the rain spacing is at 1.5. Snowflakes are at 0.5. So if I switch those on. So now in the snowflake compute shader, I've changed it slightly. Actually, I think it might be using the same one. I just changed the yeah, there's a wobble factor on it. So if we look up at the snow coming down, it's not falling straight. You know, so I'm using a cosine function to basically float the snow down. And my dog's just come in. Hello. Yeah, so we've got nice floaty snow, and it's working on the same principles as the rain. So it's lerping down from the top. But again, because the spacings are much smaller, so the spacings are at 0.5, it uses those to determine where the top of the you know, where the starting point of the snowflakes are. So again, if we look at the floor, we can see, yeah, they're getting terminated at 0, and then they get regenerated back up at the top. And then we can, all I've done then is we can add another. I'm gonna have to see to my dog in a minute. So that's all it's doing is using a different sprite really for the snowflake, which I guess if you mix them in with actual snowflakes, gives you slightly denser snowflakes. And again, we can, yeah, I'll get the rain on as well. It's raining, snowing. It's not a particularly nice day out there, is it? The rain going, hammering it down. So we could also do, so let's have a look at putting the fog on. So that's the fog on. So because we've got the fog, Unity fog functions in our shaders as well, the fog also applies to these particles as well, these particle effects. So you can see as it goes off into the distance, the fog's culling it off. And again, if we look, I mean, that's, you know, it's flying. It's not having any trouble rendering this at all. And this is in the editor as well. And the editor's having to manage all the other gubbins around it. So yeah, so we could also then add to this, I hope it doesn't blow up, the voxel renderer as well. Or is it because it's well below? yeah. Oh, there it is, which is 10 by 10 by 10 by 10. Right, that there is what's called Z-plane fighting, and it's because the geometry is on exactly the same point as the plane. So if I move that to minus 100.1, you won't get it. So there you go. So it's got fog, you got snow, you got rain, you got voxels. That's pretty cool, isn't it? So let's have a look at for example, the rain compute shader, which is there. So yeah, so I think they're all using weather generator. Yes, they're all using weather generator, just different parameters set. So let's have a look at weather generator. Actually, let's get to the weather script. Yeah, so weather shader script. Yeah, so it's a 32.32.6. So it's not, I mean, it's still a lot, but a lot of particles. So what's that, about 250,000 on each rendering? Yeah, so speed, distance, kernel again. Initialize buffers just as before. We only need start point buffer. Yeah, so it's just 4 bytes. Constant buffer 4 bytes, mod buffer 8. Yeah, so we're just setting up the buffers for the compute shader. So the constant buffer, I think I'm using that to pass in time. I could probably change that to be a regular shader parameter really, but I'll use a compute buffer there. I think that's because the example I found of a Unity compute shader online, again, I forgot the bloody source, I'm sorry if it was you, was passing it in like that, but you can pass it in as a regular param. And then the mod buffer, which I think is my starting point effectively. Yeah, so I'll basically place them. I've got like a random set of random values. I use those for against each of the points, I think, to that's the starting points, and then the mods, which is the random vector 2, so the start points, and then basically the dispatch. Actually, I could probably redo that because all that can come out of the dispatch. Oh no, I need to set that in the dispatch down. No, I don't. I could probably take that out of the dispatch. If I do the weather thing as a package, actually, I'll tidy that up. So yes, that could probably come out of the dispatch. But effectively, it's doing the same thing. So the dispatch calls calling 32x32. I've not got, which I should have, my if you can't support the compute shaders, and then the release buffers as usual, and then the start just initializes buffers just as before on post render. Now I've got it in there, not in the dispatch. Oh, dopey one. Then the dispatch method, and then point materials. Okay, and that's on post render, so that's if I was rendering it on a camera, which I'm not, so that doesn't get run anyway, so that can probably all go. So that's not getting called, ignore that, because we're calling it from a geom script anyway. And then on disable release buffers. So pretty much the same as the other compute buffers really. So then our billboard script. Oh, well, let's have a look at the actual compute shader itself. Yeah, so you've got a 16 by 16 by 1. I've got speed, wobble, wind, spacing as regular shader params. Then got the structure, the position structure, the starting Y structure, so where it is in its current starting Y position. Oh, that was it, I remember now, that's why I've set that. And then the constant structure, which is just time, and then the position modifier. So we've got a mod buffer, const struct buffer for the time, and starting positions, starting point actually on the y-axis. The mod buffer is actually where it is in the XY, I think. And then the output buffer, which is what we're actually pushing out. So very simply get, because we're only on the 1Z thread groups, that's only one, get the IDX, center it, calculate the position, and then we're going to lerp the Y based on the spacing, 32 because 16 by 16, what am I on about, 16 by 16, full, yeah, so times 32, which is going to be, yeah, the number of work threads, and then basically just over time, so between 0 and then wherever the current point is over time, multiplied by the spacing, so that'll give me the Y position. And then if there's any wobble, we can affect the position X and Z, apply any wind. You don't want the weather going, yeah, you don't want weather, good comment, don't want the weather going up, so Y is always set to reset to 0. We then offset the position by the wind and the constant buffer time over, I think I multiply by 100, otherwise you get hardly any effect on it. And then we just set the output buffer. And then the billboard script, again, just like it is actual billboard JavaScript, isn't it? Yes, it's the exact same script as we saw at the beginning, which will probably be using the billboard, exact same billboard geometry shader as well, which we'll be calling yeah, so the dispatch, yeah, because we're using compute data, it calls the dispatch every time, so we know it's a weather one. I'd set it up so you could use like a regular compute or the weather script. So that was really for my testing, that could probably go. Yeah, so effectively just the same as the other billboard. Wind. And that's pretty much it really. And as I say, in the billboard effect, yeah, you've got all the fog, apply fog stuff, so that's all in there, and that applies as well. Yeah, so there's word of warning, I guess, with using this technique to generate geometry you want to have interacting in the world, is that obviously all that geometry data is on the GPU, so none of your physics or any of that's gonna interact with that. But what I might do is, in another post, is look at creating geometry on the GPU and how we then pull it back out and get it on the CPU, so the physics systems, Unity's physics can apply physics to it effectively. One thing I did want to cover was the data. This is how I believe it works, otherwise I think it'd be really slow. So the compute data, let's go to the voxel one, has in its dispatch method gone and populated the compute buffer. Now that compute buffer, until get data is called on it, stays on the GPU, I believe. I might be wrong, but I think this is how it's working. So then when we come into our billboard or any other shader script to then use it, so output buffer, we're not doing output buffer dot get data and then passing in a load of points. We're literally saying here's the output buffer, and I think that it's still tied on the GPU. So I think in the compute shader, they're basically, the buffers are shared effectively on the graphics card. So the compute shader goes and populates that buffer, and then ends and goes off and either does it, dies or whatever it's going to do. And then the geometry shader comes on and it has got a reference to that output buffer, so it doesn't have to pull it off the GPU back to the CPU. It's staying on there, and the geometry shader just grabs and uses that output buffer. So I hope I haven't confused you anymore around computing geometry shaders. I hope it's given you some ideas what you can actually do with computing geometry shaders, and hopefully I might do some more posts on it later on. Thanks to Paul Ward for suggesting it. Paul's mad for his voxels, and I think he wanted to look at marching cubes and things like that. Whether I'll get around to doing anything like that might be quite slim, especially this side of Christmas. There probably won't be another post till the new year actually. But anyway, I hope you found it useful, and yeah, cool. Keep suggesting stuff, and I'll keep trying to write it. Thanks for watching. Oh, Merry Christmas.